Like we said, and today we're going to talk about the forward-backward embedding of directed graphs. So who was there for Thomas' presentation about Laplacian? Yes. Who remembers anything? Good. Well, so if needed, we are going to do a quick refresh at some point in the previous episode, what happened, etc. And here, so we're going to begin with a very sad observation. Is that, well, some relationships, you know, they're not reciprocal. Everything is not Facebook. So we're going to talk about directed graphs. Here, it's a simple toy example. You have a Twitter graph. So on the top, you have the superstars, like Beyonce, Ryan Gosling, everything. They have many, many followers. So you, me, anybody. I don't have a Twitter account, but maybe some of you do. How many followers do you have? No, not enough. And well, here it's Pupus on the bottom. So not as many followers as she deserves, but still she's there. And we're going to talk about the second kind of graphs. These are the bipartite graphs. So here you have two categories of nodes. So category one here, it's the characters, so Star Wars bad guys. And on the right side, the nodes are movies. So episode 4, 5, 6. And the relationship is in which episode you appear. So Greedo dies in the episode 4, so it's only connection. But Vader is in all the first trilogies, so he has three edges. Okay, so far so good. Now, if you represent that with adjacency matrices, so for a directed graph, you have a square adjacency matrix, classic. And for a bipartite graphs, you have a potentially rectangular one. So the rows are here your characters, and the columns are your movies. Okay? And Thomas has shown us many nice properties of spectral embedding last time, but he made the assumption that the graph was undirected with a nice symmetric and square adjacency matrix. So now how do we do when we have this kind of adjacencies? Okay. So first you have a naive solution. It's like, okay, I just drop the direction of my edges. And so this becomes like a Facebook graph. Like Pupus is friends with Beyonce, which is probably true, but I don't know. And on the other, you mix nodes that are characters and nodes that are movies. You completely lose the interesting structures. And so what happens for your adjacency matrix? So here, if you have a weighted graph, you're going to do your adjacency plus its transpose. If you have only binary edges, you're going to take a pointwise maximum, okay? But still, you will end up with a symmetric matrix. And for a bipartite graph, you're going to build this huge matrix, which has as many rows as you have characters plus movies. And there's going to be a huge block of 0 here, a huge block of 0 here, and then connections from the characters to the movies and from the movies to the characters here. Okay? So this is the basic thing if you're too lazy to do smart things. Less naive solution is to build the co-citation graph. So what is the co-citation graph? Is the graph where you connect two nodes if they have a common neighbor in your original graphs. And so you can normalize the weight of the edges as we're going to do here. But formally, instead of adding or concatenating your matrix with its transpose, you have a multiplication here. And in practice, when you crawl graphs on databases from scholars or everything, sometimes you find explicit co-citation graphs that have been built by people. Let's say I'm building an actors graph where two actors are connected because they have played in the same movie. So someone took the bipartite graph and built for you the co-citation graph. So,
excuse me.
Yes.
So if you have several common successors,
yes.
The weight between you two will be higher?
Depends on how you built it. Okay. On the web, some graph that you find will give you a binary co-citation graph, like it's only one for everyone. Some will just sum, like the number of the weight between actor 1 and actor 2 is going to be the total number of movies they co-starred. Here we weight by the number of by the weight of each movie. Like if everyone has played in this movie, it's going to have less influence in your weight than if you were the only two actors that starred this very specific movie. Okay, like I don't know what's this with Sandra Bullock and George Clooney, where they are the only two characters in the Gravity. And Gravity, only two actors. So being both, it's going to give you a strong connection. And Qu'est-ce qu'on a fait au bon Dieu with hundreds of actors? It's going to have a low weight, okay? And so here, if you do this weighting, you have some nice properties, which means that the degree. So this is basically just that answers your question. But then your degree in the co-citation graph, it's equal to your out degree in the original graph. Okay, so this preserves this weighting, and the consequence is that it also preserves the total mass of the graph. Okay, you're not building something that has more total weight. However, you have the weight is not distributed the same as in the original one. You have many more edges in practice because, well, you see, all the people that are following Beyoncé on Twitter will have a pairwise connection in the co-citation graphs. So there are actually 15 million of them, and a click of size 15 million, it's 10 to the power 14 edges to store. So you don't want to build the co-citation graph explicitly. You can't even store it in memory, or well, bad move to build it, okay? And for the bipartite graphs, so you see in the co-citation, the movies have disappeared, and you only have the characters that remain, which are connected through between each other. You can build the other co-citation, which is movies between them. It's completely equivalent, completely symmetric. Okay, so the co-citation graph is nice, but you don't want to build it. That's where we are right now, okay? And this is where Thomas and I arrive. So let's do just a quick refresher on linear algebra and matrix decomposition. So on the top, you have what's called the singular value decomposition, which is valid for any matrix, even if it's rectangular. So you decompose it like a matrix U, which is orthonormal. So the columns have norm 1 and are orthogonal to each other. An almost diagonal matrix that we call sigma, which is mostly 0 and then values on the diagonal, and a matrix V, which is also orthonormal, so unit norm for the columns and orthogonality. And you have this nice property that this corresponds to the standard decomposition for symmetric matrices for those matrices, so M multiplied by its transpose or the transpose multiplied by M, with here the sigma are elevated to the square, okay? But like elevating a diagonal matrix to the square, it's pretty cheap, it's not a problem. But this is the mathematics of singular value decomposition, okay? And we're going to use that. Now, we are going to define what we call the normalized adjacencies of our matrices. So it's a lot of writing, but it's pretty basic. Each time you divide by the square root of the degree on the left and on the right with the good shape so that it doesn't break your matrix-matrix product. But you normalize your rows and your columns according to the square root of the degrees of the nodes. And for those who recall the talk of Thomas, so d minus 1/2, a d minus 1/2, it's almost the Laplacian matrix, which is identity minus normalized adjacency. Okay, so we are beginning to connect to the spectral embedding. And what's nice between the original graphs and their co-citation graphs, it's that the normalized adjacencies are just a matrix product, okay? So the normalized adjacency of my complex co-citation graph, it's the product of my normalized adjacency in my original graphs and its transpose. Very simple relationship, okay? Now, what if we perform the decomposition of the original normalized adjacency matrix? So I have my row data, the adjacency, and I do, it's a partial SVD, so I only care about the first eigenvectors and the eigenvalues, the biggest one, and I decompose it like that. Then the Laplacian of my co-citation graphs, so E identity minus normalized adjacency. Well, it's very simple. It's here, my left singular vectors, a diagonal matrix that can be very simply deduced by this one. As we said, elevating a diagonal matrix to the square, it's super cheap. And again, so the eigenvectors. So this means that if I want to decompose the normalized Laplacian of my co-citation graphs as we do in standard spectral embedding, I don't have to build my heavy co-citation graphs. I can do it with the raw data only. And that's what we're going to do. So once you have that, well, you can take Thomas' talk and plug and play. The same formulas, only there you have different subscript because your degree is not the same as your in degree. But you define your embedding the same way. So you rescale the singular vectors by the degree and by nice transform on your singular values here. Okay. So here we call it the forward embedding because it's the graph that matches A transpose, but you can do everything the same with A transpose A, and then you get the backward embedding, but actually you only need to do the decomposition once because this gives you both U and V. So everything that you need to do all embeddings depending on whatever you like, only one calculation, okay? And so what was nice in spectral embedding, for those who remember Thomas' talk, is that you have all these properties. You connect to the random walk on your graph. You have your physical interpretations with energy levels. And, well, you know what you're doing. It's not deep learning, Edouard. So here, what's the random walk associated to this embedding? Actually, it's a two-hop random walk. So you have a directed graph. So you can, when you consider an edge, there's a sense, like you can go according to this direction or in the opposite direction. And the underlying walk that we consider, it's a two-hop walk, so where you do one step according to the direction of the edges, and then the second step, you take it in a reverse way. So here, Pupus is going to do the first hop towards Beyoncé with probability 0.5 because it has two neighbors here. And then once you're in Beyoncé, you go back to another follower of Beyoncé with normalized probability. So here in this graph, Beyoncé only has four followers. So you come back with probability 0.25. Okay? So that's the random walk that is hidden behind the forward-backward embedding. Okay? And now I said that we had the same properties, so you can build your transition matrix based on your original data. Same thing as for the normal standard spectral embedding. Everything's the same. Okay, and you have all the nice properties that Thomas showed for undirected graphs. You have them again for your co-citation graphs. So you can interpret the norm of two embeddings with commute time, eating times in the random walk, everything. So now the thing that you have to imagine in this forward-backward is that in the forward embedding, so you walk first towards the people that you follow, and then you come back to the people that also follow this first account. You're kind of a weighted average of the people you follow, and the people you follow, they are the weighted average of you. Okay, so that's only possible with proper scaling, but it's really a joint embedding, as I'm defined by the people I like or the movies I starred in, and these movies, in the same way, they are defined by the actors who played in that movie, or this account, the Twitter account, is defined by the people who follow it. Yeah, but all in one way. Now, how does it look when you do real experiments? So this, we use the standard Wikipedia graphs. So you have pages which are your nodes, and the edges are the hyperlinks between two pages. It builds directed graphs. And on the right side, you have the naive approach, like using, you lose the direction of the edge, and you apply your spectral clustering, and then you do your k-means with Euclidean distance. Then, like, you apply what's called spectral embedding, as in the books. And you have this ugly clustering where everyone is in the central cluster, and you have small clusters going along. Now, if you are smarter,
excuse me.
Yes.
I'm not sure I understand what exactly is represented here.
So
what is
you embed.
Red node, for example?
It's one cluster according to k-means on your embedding.
Okay, so it's a set of Wikipedia.
Yes.
Wikipedia pages.
This is the aggregated view after clustering. Okay. So on the right, it's really like from scikit-learn import spectral clustering, set cluster to n equals 8, and view aggregated results. Okay. And on the left side, it's forward-backward embedding plus the same k-means, the same clustering, but using cosine similarity instead of Euclidean distance. Yes?
But the fact that the size of the clusters are skewed on the right is not a proof that the clustering, the partition is better on the left.
Oh, you don't have any labels. It's just a regular effect that, well, you can, I have some examples later where you have ground truths, so you can say that you're better. Okay. Here it's just a qualitative view of what happens usually when you apply spectral clustering without any gloves. Okay?
Yeah, just to be sure, the red node on the right contains more Wikipedia pages than the red node on the
Yeah, it's the same scaling. No. It's just that you don't have as many different colors as you'd like. But no, there's no one-to-one matching between the colors here.
But, applying the cosine similarity on the right would balance the...
Yes, also. So Fabien, this is going to answer your question. So then you're still using scikit-learn and you go to the tutorial co-clustering. So for bipartite graphs, and you follow the tutorial and they say, okay, so naive approach, you have a rectangular matrix. So it's samples versus features. And they tell you, okay, so if it's sample versus features, you just do k-means, no embedding, and you look at the results. So no embedding is equal to identity embedding. I am equal to my raw data. And so here they are doing this example with the 20 newsgroup dataset. It's like the NIST for NLP, the small, very known dataset, not too big, rather easy to manipulate. So it's a simple dataset. You have here on the rows press articles, and the columns are words, which are transformed by a standard NLP transform TF-IDF anyway. So here an entry of your matrix is the weight of this word in this article, okay? And you know that each article has a category. So for politics, science, I think there's hardware. There are 20 categories because it's the 20 newsgroup dataset. And the goal is to find the categories in an unsupervised fashion. So first thing, I take this matrix, I plug it into k-means, and I look at the V-score, which is also known as normalized mutual information. It's the basic score for clustering. It's between 0 and 1. And so 0, you're a total loser. 1, you have a perfect clustering. Then they say, okay, we can propose you this spectral algorithm based on SVD, but it's an SVD on the normalized adjacency matrix, and that's it. Nothing more. No normalization, no cosine, nothing. So it's better already. You have a 0.44, unlike the 0.33 you had before, but it's not good. You can try to, still you go to scikit-learn, you say, okay, I'm trying spectral embedding on the big